migrations with Akka streams. I want to present basically a bit of our learnings with Scala and Akka. So with a practical use case that we did with event sourcing.
So I'm Steph. I've been working at Binder for the last 3 years and a half, and I'm working in the taxonomy team, which is the team from which we have taken this use case from.
Yeah, and I'm Leon. I'm working in the asset team, and with assets, we're basically the biggest consumer of the taxonomy team. So for today, we made a little agenda. Of course, we have a problem statement, or the start of our journey. After that, we're going to look we have a direction in mind, but where do we actually start? And of course, we're going to talk a bit about migrations with Akka streams. We also have some caveats that we run into with projections. Observability is of course also super important, and yeah, we have some final learnings. To set the context right, so what do we actually do in Binder? So in Binder, we're basically striving for brand consistency. We do that in multiple ways. So we deliver, we have tools for the creation of assets, still all the way to the distribution of assets. But today I really want to focus more on a piece that's really in the center, and that's what we call the asset bank. So this is an example of what you actually see in the asset bank. And in the asset bank, it's only mainly about 3 things. So the first thing is a search, which is all about the findability of assets. It's all about, the second thing is the storage or the behavior of assets. And the third one is actually taxonomy, and that's Steph's day-to-day job. So what we actually see here is a single asset. It has a picture and all the information that we actually here see on the right. So like terms of use, continent, country, city. That enrichment, that's what we call taxonomy. And if we take a deeper look, a separate element within the taxonomy, that's what we call a meta property, and the value we often call that meta property options. And these things are really important to us, because within Binder we don't believe that you can put files in directories. Well, we believe that you could, but that really limits the findability of your assets. So we went for this structure, and the meta properties basically define: can I actually download this asset? Can I actually view this asset? Can I actually view this single option? Meta properties can be dependent on each other. So, for example, we have here continent. If you would select this to Europe, then of course you don't want to see Canada as a country, but you want to see Belgium, Netherlands, Italy. Well, we can name all countries of Europe. Yes? Oh yeah. So you might think, oh, that looked really slick on the previous slide, but this is actually 2 of the, I believe, 5 management screens that comes around with meta properties and taxonomy in general. It's quite old. We have a huge use of data set, and we need to move away from that. So, like I said, the UI is definitely not great. All the code is really 10, 12 years old. It's written in Cold Fusion, which is developed by Adobe a long time ago. Ancient, as you noticed. And at the same time, we also get more and more requests, like, okay, what is happening with my taxonomy? Why is this meta property visible for this user, or who has changed this meta property? And there are a lot of integrations. So within assets, we have integration, but also search and other modules within our suite. Basically, is really heavily depending on the taxonomy. And with Binder, while Binder is growing really fast, we need to do more imports. And yeah, that really, we need to up our game when it comes down doing those imports. So naturally, when we were looking for a solution, we almost automatically ended with event sourcing. And event sourcing brings us also a lot of benefits. Because we suddenly get the transaction boundary, which is really, really nice. We get intents of changes. We store those, which really, really helps when clarifying what change has happened, who did it, etc. Well, we get the audit log, which also naturally comes with it. And there's more code isolation, which helps in integrations. And one of my favorite, and is also most underrated, we can project data to our needs, which is heavily underestimated, I think.
So where do we start? This is the legacy system with all the modules it contains, and it of course lives on top of one single very large database that basically all the modules use to store their data. And as you can imagine, interactions between these modules can be quite complex, and they also sometimes occur through the database. So for example, if a new required meta property is added to the system, the edit asset domain must reflect that, and in this system it occurs through the asset domain reading data directly from the taxonomy tables. On top of that, we also have an external API for the customer to integrate with our product. And so the first start is to get some functionality out. So here it's, of course, not just moving code, it's rebuilding our application on the new event, the sourced design we have chosen. And for this first iteration, we really try to identify the smallest possible use case usable for some customer with the taxonomy. So at the beginning, it would only cover around 5% of all the logic and use case we are supporting in the taxonomy system. But for this new service to be independent of the legacy, it of course needs internal database, and because we introduce a second database, we now have data duplication. So we need a data pump. The data pump is going to be the entity responsible to maintaining the sync at all times during between both systems. So basically all the modules in the legacy can remain functional even though the customer is using the new taxonomy. And in this use case, we chose to flow the data from the new to the old system. The other way around wasn't possible for multiple reasons. Like, because we only released some system that would support very few use cases for customer, like the whole data wouldn't even fit inside of the new system. And starting to trace inside of your old system which data has to be projected versus which data shouldn't be projected is going to be very complex to perform. So that's why we decided to project from the new to the old system. But that also adds an extra step in our process, which we call the migration, is getting all the data of the customer in the new system, so then the customer can use it. And finally, on top of that, we added a proxy layer on the external APIs, so then the traffic would be redirected based on what the customer is currently using, the old system or the new system. And at Binder, the way we do that is we use account features. Account features are like little switch to turn on and off feature in customer portal. And just switching this feature would basically swift the whole system to the new taxonomy. And in case of rollback need or whatever reason, we could basically bring the customer again on the legacy one. Oh, sorry. And because now the system is both usable for customer on the new and the old taxonomy, we could focus more time on building more features and supporting more use cases in the new taxonomy. And every time we would release some new feature, it would unblock more customers to be migrated. And we did that until eventually all the customers are using the new taxonomy. Then the external API can be redirected entirely on the new system. And because the data sync is kept at all time between both systems, that buys a lot more time for all the integrations that are depending on this system, even internally. So it can be also other teams, other projects, and so basically we will buy the time for everything to be switched to use with the new taxonomy. And once the whole system is depending on the new taxonomy, we can then get rid of the data pump, the code, and the data that is in the legacy system. Let's talk now about one crucial interaction between those two systems, which are the migration with Akka streams. So first, what is an Akka stream? It starts from a source, the producer, and it goes to a sink, the consumer. Then in between we can have the end processing steps that are going to be all the logic that we need to perform with our data in the application. And when you materialize the string, when you actually run it, the data will flow from the producer to the consumer. If you have a slow producer and a fast consumer, that will go very fine. Like the consumer will process items as they flow in. But if you have the other way around, a producer that is producing faster than what the consumer can handle, that's when you have issues. And for that, Akka streams have a mechanism that is called back pressure. It's basically each component being able to tell the upstream component, like, slow down, you're going too fast for me. And in our application, it looked like this. So it's basically starting from an option CSV that we're streaming. It has all the information needed for the option to be created. So a meta property ID, a name, an icon, and whatever data is needed for the application. And we have the processing steps. So is my input valid? Does the meta property exist? Is the name still available for this option? And if everything goes fine, this will end up in our system with the new event, option is imported. And we leverage this through Akka HTTP for our migrations. So we have a migration server and a user scheduling the migration for some customer. Then the migration server is going to fetch data from the legacy database as a stream, process all the data, and stream it to the taxonomy server. Then the taxonomy server will import and save everything, and will stream back in the same HTTP request the output of what has been processed. Was the option created? Was there a failure? And so we can also handle this, this processing results inside of the migration server. But let's say something is slow inside somewhere in your process, that's when the back pressure is going to be used. And so the back pressure is able to basically reach through the HTTP request your migration server. It means that the migration server, a different service, is able to adapt its processing speed to not overwhelm the receiving service that is the taxonomy server. And this is very useful to basically keep your processing at max capacity space without disturbing anything happening in the taxonomy server, which is already used by customer in production. So how was it with using Akka stream for our migration? The first learning was that back pressure is very useful to keep your processing without overloading the consumer service, but it's not 100% reliable. Like, only your processing is encapsulated in your back pressure mechanism, but you might have other interactions with other traffic or other stuff running in your application, and it would not be 100% foolproof. Then, of course, here we're talking about long-running HTTP requests, so network failure will happen. And so it was important for us to design the migration as some independent process. Like, even if we have it to run it 3 times, we are sure that the data ends up with the correct state inside of the new system. And here our processing is still kind of light, like we're just creating options and saving them. And also we can have network failure because we're talking about here an internal process to migrate data. But if you have very heavy processing in the receiving server and network failure are not an option, probably streaming with Akka HTTP is not an option here. A third learning was that ordering data when migrating was really helpful to resume the migration where it failed in case of failure, instead of having to reprocess the whole thing. And with that, we stayed at like around 200 options processed per second. We first tried a little bit initially, but we find that that was the best speed for us. And of course, this will depend on the amount of parallelism you have in your application processing everything. And if you have more back pressure in your stream, then of course it will be slower than that.
Yes, projections. So we talked a lot about what's happening on the write side. Let's take a deeper look what's happening on the read side of this. So with projection, what we're basically trying to achieve is a view based on we try to construct a view with all the events that basically is coming in. So what that view is, that really depends on your application, but you can really optimize for it. So how does that roughly work? You've got your event store where your events are stored, and they're basically going in envelopes to your projection handler. And in the envelopes there is the content of the event and the offset. And what basically happens, your projection handler receives the event, start processing it, and depending on your depending on your strategy, the offset store is basically updated. Which brings me to the first important learning. So processing strategy. So we have a few. These are not all, but these I think the three. Well, I would not say most famous one, but. We've got exactly once where we actually update the offset store after we processed one message. Then we've got at least once that happens after we update the store after each X event. And then grouped within is more like a time-based update. The most important question here is, since we're talking about legacy systems and legacy database, how well can your legacy database cope with processing the same event twice? So if you have, if you update the offset store after 5 events, then know that when your projection crashes, that you might need to reprocess 4 events again. Then there's this thing called journal slicing. Journal slicing, you can do this in 2 ways. So one is by tagging, and the other one is relatively more new, and that's event by slicing. So what we actually try to achieve here is parallelization in our projections. So, which is really nice, because if you have 1 million events that you need to process, or 9 million, you can basically divide it over multiple projections and they get basically processed. But with a legacy database, there is a huge drawback. So, while we reduce the load on the new system, we basically shift the load for like 3 days. So how did we circumvent that problem? What we basically did is we didn't care where we partitioned the data, and that means that some messages might come earlier than others. And instead for that, we made placeholder data in our projection, because we knew that eventually we will get that event that we were missing before. We know that we would get it in. So, what did we learn? We really went for the exactly once processing, because we knew that our database is not really capable of processing the same message twice, or that there are like severely more risks to it. We were also quite careful with running multiple projections. We actually did that, but we definitely also took care for the load that's on the database. And we really take a look how to balance our events in the partitions.
Which brings me to the last topic we want to cover, the observability. So of course, as every single application running in production, you want to have visibility on your system. So you must trace stuff like traffic, request status, average transaction time. But it's even more important when your system comes to have to work in parallel with the system that is already there. Like it will be our way to assess how is the new system impacting the legacy system. So for example, on the projection, are we pressuring too much the database? But can we increase the processing speed, or should we go for something a little bit slower but that is protecting the legacy system better? And in the Akka world, there are also a lot of other metrics you need to care about, like projection lag, active actors, time in mailbox, processing time of event, and a lot more metrics to trace. And for example, Leon talked about our transactional processing with the projection. And in order to keep the sync and protect the legacy database, we need the projection to fail in case something goes wrong while processing an event. But if you want to do something like that, it means that your projection will stop. And if you don't have the right metrics and alert to instantly know that something is going wrong in your system, it can be a while before you actually detect that there is an issue that needs your attention to fix. And here is an example of a tracing for a request in the whole system. So it's an API call on the new taxonomy for option creation as batch. And so we see that basically we have some routing to the new taxonomy, then the taxonomy handles its logic, handles command, start actor, and responds that option have been processed successfully after 200 milliseconds. And that's our HTTP response time. And in the lower part of the screen, you actually see the projection starting to handle these events. So after a second and a half, we see that the projection is going to be projected in the legacy database, update our Solar search engine, and then doing other logic that we need. And here, this kind of metric gives us an overview of our eventual consistency of the new system with the old one. So it means that the data will reach the old system after a second and a half. Is that good enough? Do we need to improve that? But again, you need to have the visibility to be able to take the right decision to improve your new system and know what's happening inside of it. So what about your system? What are our learnings in this journey? So first, event sourcing is not easy and will probably require iteration. Especially for a company like ours, we originally come from the Python world, and now this was the first interaction with from my team to work on the Akka distributed system like that. And so it's, I think, one of the main reasons that this project is now running in production and able to handle our traffic is that we decided to release very early, and along the way validate, iterate, test, see how the system is reacting, and like to find maybe some mistake in our design and fix them along the way and improve the system. So really the decision to release early and have traffic from the start was really key in this project. Instead of like working on it for years and years, then reaching production, then you send the traffic on it, and then you have surprises. But if you go for an iterative approach like that, it's also very important to identify the architectural choices that aren't going to be easy to change later on. So for example, if your events are not designed well and you need to change your flow into the events, it's going to be very hard to do. And it's going to basically stick with you for a while. So get the event right and focus on this part of the system. And then the final learning of this journey is that tracing metrics are crucial to be able to understand what's happening in your system, and even more in an event sourcing system than any other one. And if you care about developing your dashboard when you actually need it, it's probably too late, and you should make sure to have this visibility from the start on your system. So thank you very much for listening.
Hi, thank you for the presentation. I know that there was a bit of a drama with Akka licensing change. How did it affect you?
Yeah, so for us, this is a known problem. So what we actually do, we are more or less forced to move to PECO, especially our US clients. Well, there's this SOC 2 compliancy, what's now really big for those US clients, and one part there is how we deal with security issues. And yeah, PECO, well, Akka doesn't solve the security issues anymore, so that way we are basically forced to move to PECO.
Thank you.
Maybe also what is worth to note is that currently there is no way to migrate from Akka to PECO without downtime, because you need to update internal queues and everything. So basically we're working on it, but it's not that straightforward. It still needs to plan a time to migrate outside of like high traffic time, and so yeah, it's a work that we're currently planning.
And it's a tedious job, I can say.
Thanks a lot for concise and visual presentation. We like it all. And could you please elaborate more about taxonomy, because it's a sign of really maturity of your understanding problem. Maybe Scala asks for concise, valid data modeling. How do you do it? How do you manage the compatibility of versions of taxonomy? What is taxonomy in your case? Of course, without disclosure some secret information, I would like to hear it. Thanks a lot.